Hey guys, Mr. Rast here. I was just reminiscing about college and some of those college assignments I had, and I remember one time I had a professor ask me to write an essay on acid, and the darndest thing happened. My pen turned into a lightsaber, and my paper was chasing me around the room, trying to eat me. I'm just kidding. Don't do drugs, guys. Don't do drugs. You got one body, and you're stuck in it, so treat it well. So what are we talking about with the second lesson in topic 8? We are talking about empirical formulas. And in the first lesson, we talked about percent composition. So if I told you a compound, a molecule at this point, you should be able to tell me the percent composition of all the atoms in it. For instance, if I asked you to tell me what percent composition there is of hydrogen in water, you could calculate that. What percentage of oxygen is in water, you could calculate that, and that is again by mass. Empirical formulas is going the opposite way. So if I was to tell you that there's a substance that has a certain percentage of hydrogen, a certain percentage of oxygen, you would then tell me the formula for it. So we're going to go the opposite way than what we did in the last lesson. It's the same mechanics, it's the same kind of math. It can be a little tricky, so pay attention, hold on tight, take notes, get your periodic table out and a calculator, and let's roll. Okay, so when we talk about formulas up to this point, I've been showing you molecular formulas. The molecular formula shows you the kind and total number of atoms in a molecule, such as H2O, water, has 2 hydrogens and 2 oxygens. You're used to seeing a molecular formula. Empirical formula is a little bit different sometimes. So let me just tell you, an empirical formula is telling you the proportions of the elements present in a compound, but it's not necessarily the actual numbers, and it's not necessarily the arrangement of the atoms. It's just telling you the proportions. And so let me give you some examples of the difference between a molecular formula and an empirical formula. So P4O10, that would be a molecular formula that we're used to. The empirical formula is just telling you the proportions of them. So the molecular formula is saying that there's 4 phosphorus and 10 oxygens in this molecule. So, but the proportions of it would be that it's a 2 to 5 ratio, that there's 2 phosphorus for 5 oxygens. I think simply put, an empirical formula is the formula most reduced. If you can reduce it to the lowest common factors, that would be your empirical formula. So sometimes your molecular formula is an empirical formula. In other words, you can't reduce it anymore, such as with water. H2O, you can't reduce this anymore, so the empirical formula sometimes is the molecular formula, but like in the last example, it doesn't necessarily have to be so. Let's take a look at another one, N2O4. We could reduce this by dividing both the subscripts by 2, and that would make the empirical formula NO2, which is nitrogen dioxide. Some of my students were real sharp to point out, they were thinking, hey, that looks like nitrite. Nitrite is NO2 negative. This is a molecule, and I'm proud of you guys for picking up that it looks a lot like nitrite, but because there's no charge, this is just nitrogen dioxide. Let's take a look at another one. C10H22. We could reduce both of these, and the only thing that actually can go into both 10 and 22 is 2, so that would reduce this to C5H11. Another one, C5H12O. Now, this is a little tricky. If you think about it, you can't reduce anymore because that oxygen is there's just one, so we can't reduce this anymore. So the empirical formula, again, like water, is the same as the molecular formula. And let's do one more. This is C6H12O6, which is the molecular formula for glucose. Glucose is a monomer of sugar, the most simplest of sugars. When you connect multiples of these guys together, you get something like sucrose, which is 2 of these put together, so it's twice as big. Lactose is another one with 2 of them. You can connect a large chain of them, and you can get things like starch or fiber or galactose. Actually, that's not galactose, but you can glycogen. I'm thinking glycogen, long chains. But regardless, they reduce down into this structure, and the reduced empirical formula for these sugars is CH2O. Notice there's a carbon for every one water, and therefore this structure here, these sugars, are often referred to as carbohydrates because of the empirical formula for them. Okay, so if I gave you the percentages, or I gave you the quantities of what's in a compound, and I'm asking you to give me the empirical formula, there's 4 steps that we're going to go through, and I'm going to explain these right now, and I would suggest just jotting them down and referring to them, but I will walk you through using these 4 steps with an actual example. So the first step is to start with the number of grams of each element given in the problem. If you're not given grams, if you're giving percentages, you can take a percent of anything, but the easiest thing to do would be to take a percentage and just assume 100 grams. Therefore, your percentages will actually just be equal to grams. The next thing is convert the mass of each element into moles using the molar mass on the periodic table. So, and if you're not comfortable with this, please go back to lesson 1 in section 8. Our topic 8, lesson 1, and we did these conversions of grams to moles and moles to grams. So you should be familiar with this, and I'll kind of go through this quickly when I do these examples. If you need more practice, again, go back to lesson 1. So convert the mass of each element using moles, using the molar mass from the periodic table. The third thing, this is a little bit confusing, but when I walk you through this, this will make sense. Once you've converted all of the grams into moles, then you're going to take your smallest value, whatever you have the least amount of moles, and divide each value by that number. So whatever your smallest value is, you're going to divide each of those answers by that number. Okay. Once you got those numbers, you're going to round to the nearest whole number. You're going to try to get these numbers to, so you're going to divide them all, and you're going to try to get the smallest whole number that you possibly can for these. And these whole numbers are the subscripts for your empirical formula. Just a note, and this will make more sense as we go through this, when you're rounding, if rounding it to the nearest tenth doesn't give you a whole number, so you might have like 1.99. When you round that off to the nearest tenth, that 9 rounds this 9 up. I'll just show you over here what I mean by that, rounding to the nearest whole number. So if you have a number like 1.99, rounding to the nearest tenth, this rounds this up here to a 2.0, which you're going to go to the nearest whole number would just be a 2. Okay, that's what I mean by that last step. Okay. If it doesn't go to the nearest tenth, it doesn't go to a whole number, let's say you have something like 1.5, then what you're going to do is you're going to multiply every single one of your answers, every one of those subscripts, by 2, so that this 1.5 will become a whole number, become 3. You can also, another example, like if you have 1.25, then you can multiply everything by 4 to make this a whole number. So if you don't get a whole number when you round off to the 10th, you're going to have to multiply everything so that you do get a whole number. All right, it's actually a lot easier than it sounds right now. Let's take a look at an example right now. So a compound is analyzed and found to contain 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. What would the empirical formula for the compound be? This is a great test question, okay? So what you first do, if we look back at your steps, we talked about 4 steps. We're going to walk through those right now. The first thing you would do is take what's given and get it into grams. Nice thing is it is already in grams. If it was in percentages, just make those percentages grams. Assume 100 grams, and then it would just fit right there. So we just take out what's given here. We've got 13.5 grams of calcium, 10.8 grams of oxygen, and 0.675 grams of hydrogen. The second thing you're going to do is convert all of these values of grams into moles. And you might want to stop the video here and try this on your own, kind of just reinforce what you've already learned about converting grams to moles. So you might want to stop and see if you can convert these 3 things, calcium, oxygen, hydrogen, into moles. All right, hopefully you did that and you got a shot. The first one, I got 0.337 moles of calcium, and how you do that again is you take the mass, so I've got grams, and I'm going to multiply it by the molar mass, but I'm going to invert this either grams as my denominator or my numerator. Because I'm starting with grams, I want grams to be my denominator because I'm always setting up to cancel. So I cancel out my grams, I've converted it into moles. I got for oxygen, I got 0.675 moles. And for hydrogen, I got 0.668 moles. Again, if this was a little challenging for you, go back to the topic 8, lesson 1, and that's where we really did these conversions in more detail, a more detailed explanation to that. So anyways, this is the second step. I've got converted everything into moles. The third step was to take my smallest answer and divide each one of them by that. My smallest answer, let's see. Well, calcium, I've got 0.337. Oxygen, I got 0.675. Hydrogen, I got 0.668. My smallest answer is calcium. So my third step is to divide each mole value by the smallest number of moles calculated and round to the nearest whole number. So if I'm going to divide calcium by the smallest number, it's just 1, right? Because one of them is always going to be 1, by the way, because the smallest one will be 1. If I take oxygen and divide it by the smallest whole number, I get 2. And if you try the last one, hydrogen divided by the smallest number, I get 1.98. And like I was just saying, try to round this off to the closest tenth. So this 8 rounds the 9 up to a 10, which rounds the 1 up to a 2.0. So that is, smallest whole number is a 2. Now these are actually the subscripts for our empirical formula. So that's the fourth thing you do, is you're just going to write the empirical formula with these subscripts. So this is saying that I've got 1 calcium, and I've got 2 oxygens, and I've got 2 hydrogens. This is the ratio, the proportion of everything in this compound. So to write the empirical formula for that, I'm going to take those values, and I've got 1 calcium to 2 oxygens, which is related to 2 hydrogens. So most likely this is calcium hydroxide. This part here that I have in bold is all you have to do, okay? 1 calcium, 2 oxygens, 2 hydrogens. You don't have to try to predict what it actually is, but I think you should understand this now after what we've gone through with ionic compounds and whatnot. Okay? So our workshop for this is just practicing this. I want you guys to try to convert or to try to get the empirical formulas for these following problems. So you're just going to, again, this is a copper and an oxygen. You got 44 grams of copper and 5.6 grams of oxygen. You're going to first convert these grams into moles, and then whichever one has the smallest amount of moles, you're going to divide both of them by it. So one of them is going to be 1 because you're dividing it by itself. Divide the other one, and if they come out to whole numbers, that is your ratio, and you write the formula. If it doesn't, you're going to multiply through to get them to be whole numbers. And I will go over examples with that, and we'll do that in class. Do your best on this. Save any questions you have for class, and so that we can help you. And that's what I'm here for, guys. I enjoy it. So good luck.